No, bad boy, it's Sunday. Yeah. Well, the AP exam doesn't care what day it is. Unfortunately. Boop, boop, boop. My board not working today? Oh. There we go. What's up, Alexandria? Happy Sunday. Got some cool Unit 6 questions. A lot of simple harmonic motion, I guess. Coach G. What's up, Coach G? I'll give everyone like five minutes before I start stuff off. Yeah. Also trying to find. I wanted to like talk. Peg usually. One where they have. I can hear you. Well, that's good. That's good. You can hear me, Ethan. Is my mic muted? I hope my mic is not muted. Yeah, I was just. Y'all always tell me if there's any sort of audio issue. Cool. I like this one. Your. I can hear. Yeah, what's up, Sensation Black? How was the coronation? You guys all watch it? You know, big thing in England. Super blurry. I guess it's okay. It'll work. Okay, cool. I wish it was Diana. Yeah, I know. Yeah. Although they were, what's her name? Who's the princess now these days? Face's wife. Royal coronation. The Princess of Wales, right? Is that like name? Yeah, This is it, right? Princess Kate. That's what it is. There was a cool picture. It was her daughter, I think. Yeah, this picture. This reminds me of something out of like, I don't know, like Star Wars. I feel like this is like Princess Leia or something. Yeah, this is what. Yeah, right. She looks like Leia from the new Obi-Wan series. Oh yeah, yeah. People get all. I had some people getting all mad about it or whatnot, and then not mad about it. And just, people are always gonna find something to get mad about. I think it's cool. Traditions are fun. You know, I get it that the monarchy is probably not the nicest tradition sometimes for certain people that got colonized, but it's still cool for them to play dress up, I guess. All right, cool. Let's start off some physics here. All right, welcome everyone to Office Hours. My name is Dr. Gold. This is Actual Education. We are prepping for the AP Physics 1 exam. So last session, we went through a bunch of the free response questions on a previous year's exam. And I thought a good idea for today's stream would be to just kind of like patch up any of the holes that you guys, in the audience might like have. You have like, for instance, I'm kind of weak on simple harmonic motion, or I don't really understand Newton's laws, or like friction always, gets me. Now's the time to like go through it. I will answer any questions for the next. Yes, I don't know. Maybe I'll do 2 hours. We'll see how far I make it. Must have allergies. Those are like all messed up. But okay. Let's see. So I remember Alexander, you were talking earlier about how like Unit 6 was stuff that like you kind of wanted to help with. I thought maybe I could like get some problems for that. So let's see. Tool. Yeah, send them. Yeah. I think you should be able to drop them in the chat. Let me know if you can. Or you can always just DM them to me. And what this will do is this will help other people. Other people who are watching, you're probably gonna learn something along the way. It's like by helping you, we help others. Yeah, sensation as opposed to people who have called themselves president in the past 100 years, tyrants, one and all. Yeah, I know. People say I should run for president. I don't know. I could fix some things. I don't know. I hate playing the game of politics. That's actually the whole reason I got into physics, is I thought that there wouldn't be any politics in physics, and then I was wrong. Because there definitely is politics with it. Talk to anyone who writes grants. A lot of politics. Anyways, this is kind of a cool question here. They say, if it takes a particle in simple harmonic motion 0.5 seconds to travel from the equilibrium position to the first maximum displacement amplitude, what is the period and frequency of the oscillating particle? Oh, okay. Well, it's not too bad. This is kind of more of like a conceptual question. So we'll get into some more. So what they're saying is that if you have a particle, that simple harmonic motion always looks something like this. And this is an equation which is equal to sine of, I think it's kx plus omega t, or sorry, it's omega t minus kx. This is like the full equation for y as a function of x and t. We call this like two-dimensional. And then this is for particles that are moving to the right. The minus sign always means. Anyways, so they say it takes 0.5 seconds to travel from the equilibrium position to the first maximum displacement. That's right here. Okay, cool. That we know is 0.5. No, this is 0.5 of a second. And they want to know the period. Well, the cool thing about simple harmonic motion is that the period is equal to 1 full cycle. So that's going from here to here. And the amount of time it takes for it to go up to the first max, that's a quarter of a cycle. Because then half a cycle would be coming back to the equilibrium, 3/4 coming to here, and then 4/4 or full cycles coming. So this is pretty easy. This one you can just say multiply it by 4. And then the frequency is related to 1 over period. So this ends up equaling 1/2 hertz. So very, 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 very good fundamental, but not too. Okay, cool. I like this one. Or here, let's pull Alexandria's. Good. Okay. Wow, they love the text. People write like essays when they ask you guys. Fortunate. Okay. Let's see if I can make let's see if I can make this big enough for you. Okay. Okay, a block on a horizontal surface is attached to a horizontal spring of negligible mass as shown. Okay. At the end of the wall, there's negligible friction between the block and the horizontal surface. A group of students wants to investigate how stretching the spring within the block spring system influences the motion of the system. For each the spring is stretched a distance x, shown in figure 2, and then different masses are okay. In one experiment, the students allow the block to oscillate after stretching this distance a. Potential energy is you. Then what is the change in kinetic energy of the block after it's released and it has traveled a distance of a over 2? Ah, okay. Cool. Good. Okay. So, yeah. What we have here is we have, I'll draw some like better pictures of this. We have a spring, right? Attached to a mass. And then what happens is we're going to pull that mass out a distance, A, what we say. A is also stands for like amplitude. And this is cool because when they release this spring, release this mass from the spring, it's also going to then oscillate back to its original position, but then also it's going to oscillate inwards to compress the spring, and it's going to also do that a distance A. So we say that the block will oscillate between these two positions. Okay? Now, what they're asking is, what is the change in kinetic energy when the block has traveled a distance which is going to be a over 2? Okay. So here's some cool things to know. When the block is at its maximum displacement, okay, this is when the spring potential energy is going to be maximum. So this is the whole mechanical energy thing we were talking about yesterday. So total mechanical energy, which is always conserved, say like constant, is going to be equal to the spring potential energy plus the kinetic energy of the block. If this thing was going up and down, we'd also have the gravitational potential energy, but we don't have that. This thing is flat. Exercises for asymptotes. Here, I can do something for asymptotes. Asymptotes are actually kind of a prick. Okay. So when the block is at the furthest amplitude to the right, that's when the potential energy of the spring is going to be the greatest. Okay. And the equations we know for this is equal to 1/2 k delta x squared, whereas this is equal to 1/2 mv squared. And the sum of these things has to be what we're going to call like E total. So when this spring is at its equilibrium position, this is going to be the least. That goes away. But the total energy, right, has to always be conserved. So that means your kinetic energy ends up being the most. When the block is at one of its extremes, either like it's compressed in the most or it's stretched out the most, this is going to end up being very big. And the biggest this can get is for this to be 0. The important thing to note here is that kinetic energy can never be negative because you have V squared. So even though V will point in different directions, right, to the left and to the right, as this thing moves, V squared will make it so that this number is always positive. So, anyways, okay, so they said after stretching a distance A, the potential energy in the spring is U0. All right. So we know that when delta x is equal to A, that the total energy, that the potential energy stored in the spring is going to be U0. And once the thing is stretched at its maximum distance, it's also assumed to be at rest. So this is assumed to be 0. And so this is going to be that U0 which is the total energy stored in the spring, which is the total energy in the whole system when it's being stretched out. This is equal to 1/2 k a squared. All right. Now they want to know what is the change in kinetic energy when it's released from rest. Again, the from rest is key here. That's why this started with 0 velocity. After it's traveled a distance a over 2. Okay. So what you're going to have, you look at, for instance, this is US KE. We start out with some initial U0. This is at X A. And, B is going to equal to 0 here because it's at rest. But as it starts to move inwards, some of this potential energy in the spring is going to transfer into kinetic energy because the thing is going to be moving. And, once it has a velocity, that has kinetic energy. But the total energy has to be the same. So what ends up happening is there's like kind of a transfer of energy here from US AE. But the total of these two things has to still equal the total energy at the beginning, which was U0. So what I'm going to say here now is that U0, total energy, is equal to 1/2 k. This is going to be a over 2 squared, right? Delta x is going to be the amplitude divided by 2 now. And then this is now going to be plus ke. So in the first case here, ke was 0. Now ke is not going to be 0, right? Ke is going to be something. Right? So we can solve for this, right? And okay, so this is going to be U0 is equal to 1/2 k a squared, and then this is going to be over 4 because the 2 squared here is going to make this a 1, and then this is plus ke. Okay. Now, kind of a cool thing to note here, right, is that they want to know the change in kinetic energy. So kinetic energy is going from 0 to whatever this value is. So we can solve now for what the new kinetic. If we move everything here to the left, I have this is U0 minus 1/4 of 1/2 k a squared is equal to let's say like ke new. That's the new. Now, at the beginning here, right, mu0, right, which was the initial spring potential energy, that was 1/2 ka squared, which we notice here in our equation, right? We have 1/2 ka squared again, right? This is also mu0. So what we end up having is this is mu0 minus 1/4 mu0 is equal to ke, which is going to be 3/4 mu0. Okay. So what happened is the kinetic energy went from being 0 to being 3/4 of the initial spring energy. So if we wanted to like draw our diagram here correct, actually, right? This would end up being like 1/4 mu0, and this would end up being 3/4 U0. And together, they still add up to U0. Yeah, you see that? Yeah. Yeah, what's up, Noise? Noise, we're doing physics. Your favorite class, besides statistics. Yeah, that one's kind of tricky, Alexandra. Yeah, right? Because I think this is the thing they wanted you to know. They want you to put it in terms of U0, right? Almost got tricky. Yeah, thank you so much. Yeah, they did, right? Yeah. Because I think they wanted it, what is the change in the energy? Well, they didn't say here, but they usually want it in terms of U0, yeah. So, yeah, that's a pretty cool one. Uh-huh. Yeah. Main thing being that, like, the spring energy, right, goes as 1/2, we say, like, k delta x squared. So if this drops by a factor of, if delta x drops by a factor of 2, the entire potential energy drops by a factor of 4, so 1/4. So the kinetic energy then has to go up, right, to the 3/4 to Wagwan. All right, nice. That's a pretty good one. Let's see. These are all just oscillations. With the period of a pendulum. Oh, I like this one. Dun, 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 dun. Okay. Does AP Physics 1 do simple harmonic motion? It does noise. Yeah, and that's just what we were doing. We were just doing this was a simple harmonics motion. Yeah. Okay. This is another one with simple harmonic motion, dealing with like pendulums. Do you guys know the equations for pendulums? It's only like 4% of the exam though, thankfully. Oh, that is nice. Yeah. I remember the breakdown. There's like there's a breakdown of the topics once. Like AP 1 topic breakdown. Yeah, the FRQs are. Yeah, here we go. Here's all the percentages they do it. Yeah, see, they say on the exam 4 to 6% is simple harmonic motion. But I feel like sometimes the entire FRQ is simple harmonic motion, and that's like a big part. Torque is actually a lot. Oh, okay, that's cool. Yeah, right? They say it's 4%, but then if it's a whole FRQ question, that's more than 4% of your exam. Momentum is a lot, yeah, for sure. Energy should be a lot, yeah. Dynamic. They got rid of the circuits, actually, on it, which is interesting. Back in 2016, you used to have to also do circuits. Yeah, work and energy is fun sometimes, yeah. It's cool to see how, like, work and energy can solve physics questions that you would usually need, like, kinematics equations for. Yeah. Noise. Yes, I drank a lot of Malibu. That stuff is too sweet. Noise. What are you doing drinking sugar drinks? Yeah, okay, cool. Yeah. Let's see here when they talk about like pendulums. Do you guys know half the exam can do when you work if it doesn't specify? Yeah, right, yeah. You know what's very cool, Alexandria? If you get to higher levels of physics, for instance, at like the undergrad and like graduate level, you start learning about things called Lagrangians and Hamiltonians, which you can then use to solve even more like huge broad array of like mechanics questions. And it becomes like a super powerful tool. I feel like AP Physics 1 is just the mechanics part of my A-level course. Yeah, it pretty much is, but it's also algebra-based, which is interesting. You're not supposed to use calculus, which to me is, like, weird, because calculus was invented for physics, you know? It's kind of a... All right, let's see. Period of a pendulum in an upward accelerating increase or decrease with an elevator moving with constant motion. Okay, cool. It's kind of like a trick question here. So what you guys learn, right, is that the I believe it's the period of oscillation for a pendulum is at 2 pi square root of L over G. I have to remember. Give you a nice equation. Yes, there we go. Pendulum. 2 pi square root of L over G. Okay. This is, right, the length of the pendulum. This is the acceleration due to gravity of the pendulum. Or we say, like, the rest frame acceleration of. An important thing to note here is that the period of oscillation for a pendulum that's going, right, back and forth does not depend on the mass. So if they try to, like, say, like, oh, we double the mass, what happens to the period with a pendulum? It does not change. This is different than, for instance, springs. Springs, the mass does matter, right? Because we have that T is equal to 2 pi square root of M over K. In this case for springs, you know, look out here, which is if they say the mass is changing for a spring system, that will change the period of oscillation. With pendulums, they don't. The only things that can change it is the length of the pendulum, or if the gravity that it's experiencing changes. And the reason for that is the gravity can be thought of as like the restoring force, okay? Where, you know, if a pendulum swings from left to right and whatnot, gravity is what is like pulling it to the left and the right. And if you're in situations where the force of gravity is different, then that's going to change how fast your pendulum moves. Yeah, physics is awesome. Okay, but they say we're in an elevator moving with constant motion. A key thing here when they say constant motion, you guys should always notice real quick here, this means acceleration is equal to 0. Okay. So, the acceleration of the frame, right, is not changing. They love to do these with elevator questions. So this is a good review question here. Let's say I'm in an elevator, okay, standing here, right? And the elevator is accelerating upwards. Let's say it's accelerating upwards at 4 meters per second squared. And let's say I weigh, I don't know, a good day, I weigh 100 kilograms. How heavy do I feel in the elevator? This is a good dynamics question. Do you know what this one is, Alexandria? Do you know how you solve this one? They love to do these. Okay, that's okay. You always get confused. Totally cool. Let's unconfuse you. Yeah, right? I definitely understand everything in that equation, and I agree 100% with the solution. Thank you, Arnold. Okay, all right. So here's the key thing, Alexandria. Whenever we're doing like elevator questions and whatnot, and they say like, how heavy do I feel? This heaviness that we say that one feels, this is always equal to what's called the normal force. Okay. How heavy you feel and what a scale reads when you stand on a scale and you see like a number or whatnot, that is always reading the normal force on the scale. So if we were to draw a force diagram for the person here, okay, so let's do a little force diagram here, okay. There's always the force of gravity pulling down, which is going to equal to mg. And then there's always the normal force pointing up, okay. And what we know here, right, is that the sum of these forces, which is going to be equal to Fn minus mg, or Fg, right? This always has to equal ma, all right? Yeah. So in the case that this person has no acceleration, so their velocity is not changing, so this can be either at a constant speed or the elevator is just standing still, this ends up being 0, right? And if this is 0, you're right, equal and opposite. Fn is equal to Fg. Equal and opposite, right? You end up getting Fn is equal to Fg. Very good. Right. So in that case, the normal force, which is how heavy you feel, is just equal to the force of gravity. So this would be 100 times 9.8. So yeah, the normal force would feel 980 newtons. And, you know, saying how heavy you weigh in newtons doesn't really do much good. So what we always do is we kind of put this in like what we call like a mass equivalent. Because this is just m times 9.8, right? So it's the equivalent mass of 100 kilograms. But, you know, that makes sense. You know, the elevator's not moving. I'm going to weigh as heavy as I should weigh, right? But am I on Twitch? I am on Twitch, Arns. Here's my Twitch if you want. Education. We also stream on Discord. Now, let's say that the elevator is accelerating upwards, okay? So this has an acceleration in the up direction, okay? Now, this MA for the whole system, the person on the elevator and whatnot, this is positive, okay? Because A is no longer 0. So in this case, I now have that Fn minus Fg is going to equal to my 100, the mass, times a positive 4. Okay, so this is now a positive number. Okay, if Fn minus Fg is positive, what does that tell you about Fn compared to Fg? Which one is bigger? Good. Yeah, Fn is now greater than Fg. Because big number minus smaller number gets you a positive number, right? Great, exactly. So you can solve for this. You get that, okay, Fn is then going to equal, if we move Fg over, that's Fg plus 400. So this is going to end up being, Fg, remember, was 980, 9.8, okay. So I get Fn is equal to 1380 newtons, okay? So now the normal force, 1380, is greater than what it used to be. It used to be 980. So the person does feel heavier. And if you want to know, like, the equivalent weight of, like, how heavy they feel, you can always just take this number and then just divide it by G. So if we do 1380 divided by 9.8, where's my calculator? Oh. There we go. Yes, okay. So if we do 1380 here, divided by 9.8, then this person is going to feel as if they were 141 kilograms. They're going to feel, you know, almost like 40% heavier. Yeah, they just use 10. Yeah, that's too funny. Like, you know, G is equal to technically 9.81. That's like what I think is proper. But then, like, I'm okay with 9.8. But then when they just start saying it equals to 10, I'm just like, what? Noise. This is kind of, dude, I weigh 100 kilograms. Yeah, well, it depends on your yeah. Sometimes in physics, they'll start saying, like, oh, everything is just equal to okay. So yes, so if there is positive acceleration, then you are going to feel heavier because Fn is going to be greater. This has to be greater than Fg. Okay. Now, if the acceleration was negative, okay, so, like, you know, let's pretend that now acceleration is negative. Let's say A is the negative 4 meters per second. Okay. Then we still have our same situation. Box. Okay. Now, this is going to be negative. And if this is negative, we can say, what about Fn and Fg, right? So here's actually the cool thing. Fg never changes, right? The force of gravity doesn't matter, like, how fast you're accelerating and whatnot. It's always the same. But in order for now this to be negative, Fn is going to have to be less than Fg. Which is why you feel lighter when the acceleration is negative. And again, you can solve for this. So this would be Fn is equal to, move this over, this is 980 minus 400. And so this would be equal to 580. Which, again, if you want to know the apparent weight, divide by 9.8. That gets you 580 divided by 9.8. And that's 59 kilograms. So pretty light, actually. You guys have probably seen this in, like, real life. If you've ever been in an elevator and, like, you jump right as you get to the top, whatnot, that's why you end up feeling like kind of like weightless. You feel the effect of you weighing less because as the elevator is slowing down towards the top, the acceleration is negative because the velocity is changing from positive to 0, and your apparent weight being less means that you feel like you can jump higher. It's kind of it's a concept. But yeah, hopefully this makes more sense. Where things can get tricky is the direction of the acceleration. So kind of some key little hints here, right? Is if something is going up and slowing down, then the velocity is going from positive to less positive. Okay, so this is going to be acceleration is. And also in the same case, if something is going down and speeding up, this is an initial velocity that's negative to something that's more negative. This is also acceleration. This is like velocity. And the opposite is true, right? If it's going up and speeding up, then the acceleration is positive. And if it's going down and speeding down, that's going to also be positive acceleration. I used to always get those confused. Hopefully those. Okay. Let's see. I want to try doing this block equation. You guys tell me if this one's helpful. Okay, so they say we have 2 blocks are stacked on top of each other. The top block is attached to a nearby wall. Here, a little bigger. With a string. Assume you're pulling the bottom block this way to the right with a constant speed. And they ask, what is the frictional force between the bottom block and the floor? What is the frictional force between the 2 blocks pulling? So, like, what's the frictional force between these two? And then what is the total force I need to pull on the bottom block? Okay, and this is cool. They give you the coefficients of friction as being 0.3 for both sides. Okay. This is a tricky one because you have multiple block systems, and it can be hard to isolate each block when you're drawing the free body diagram. The beautiful example of this one is actually here. Let's do another intro. Let's say, for instance, I have 3 blocks of mass 10 kilograms, 20 kilograms, and 5 kilograms. I push, and let's say that are attached, that are touching each other. I push to the right with a force of, let's say, 50 newtons. What is the acceleration? Blocks. Okay. So let's say we got a 10 one here. We got 21 here, and then we have a smaller one here. 5. Okay. And I'm pushing, right, with a force in this direction of 50 newtons. And they want to know what's the acceleration of all the blocks. Okay. There's a shortcut to this. The shortcut you can use is that if all of these blocks are kind of like stuck to each other, right, because I'm pushing on this one, and then it's pushing on this one, it's pushing on this one, and they don't separate, you can treat this whole thing as a single block of mass 35 kilograms. And then this is a simple diagram of, like, I have 50 newtons. So sum of F, which is 50 newtons, equal to the mass, the total mass, which is 35 kilograms, times the acceleration. And you can solve for A. A is just 50, which 1.4. Okay. But if I wanted to draw the force diagrams on each one of these, this is a good exercise in doing things. Because a lot of times students get this wrong. So let me just go over real quick how this works, and then that'll help us with the next question. So if this block is 10 kilograms, okay, let's look at the 10 kilogram block, and I want to describe the forces on this block. I'm only going to look at what the forces are acting on this block, which in this case, this block directly feels the 50 newtons. So we would say this is the pushing force of 50 newtons to the right, okay? And then it also has the normal force, and it's going to have the force of gravity, okay? If we look at the 20, and actually here, yeah, I'm going to get to it. I'm missing one force here, but I'll show you on the next one where that one comes. If we look at, for instance, the 20 kilogram block, right? Some students are tempted to say that, oh, this thing must feel also the pushing force of 50 newtons. And like, no. The 20 kilogram block is not being pushed directly by the 50 newtons. What's actually happening is that okay, let's label this block 1, block 2, block 3. The 20 kilogram block is feeling a force from the 1 block on it. So we say this is equal to F1 on 2. Or sometimes what they'll say is like F1, 2. Okay? And it still has the force of gravity. And however, so there's a thing in Newton's laws that deals with what are called force pairs, which means that for every force, there's an equal and opposite force in the other direction. So if this second block, right, is feeling block 1 pushing on it with this F1 on 2, block 1 must be feeling the equal and opposite force of 2 pushing back on it. So this is the same thing as F2 on 1. Like I say F2 1. And the key thing here is that these are the same. Okay? So between these two blocks, this 10 kilogram block, as it's being pushed forward, feels the 20 kilogram block pushing back on it. And by the same measure, the 20 kilogram block feels the first block pushing on it. And these forces are equal to each other. We say like F21 is equal to F2. Now in the 20 kilogram block, right, that also means that it's going to feel a force from the third block. So that's going to also feel, from here, this is going to feel, oh, thanks for the follow. This is going to feel F3 on 2. Because if we look at our third block here, which is the 5 kilogram block, this also has, right, force of gravity, normal force. It's going to feel F3 on 2. But also, it feels, sorry, no, that's wrong. Yes, no, that's right. F3 on 2. Yes. Or F2 on 3 is what we say. Second block acting on the third block is going to push the third block to the right. And then it also has the opposite of this direction. Or actually, no, it doesn't have any it doesn't have any force left because there's no other block in front of it pushing it backwards. It just has this. Okay, cool. All right. Yes, good. We have our pairs. This is also a pair. We say, for instance, here that F3 on 2 is equal to F2 on 3. So if we add up all the forces here for each block, okay? And let's not worry about the y direction stuff because everything is staying on a flat ground, so we don't have to worry about that. But if we're just looking in the horizontal direction, okay? For block 1, that would be Fp minus F21 is equal to the first block mass times acceleration. For the second block, this would be F12 minus F32 is equal to the second block mass times acceleration. And then this one would just be F23 equal to the mass of the third block times its acceleration. And then the key thing here is that if all these blocks are stuck to each other while they're moving, all of these accelerations are the same, okay? Which is kind of nice, because that's gonna help us like solve for things. So this is technically A1, A2, A3, but A1 equals A2 equals A3. So we can just kind of get rid of it and just say, okay, we're just gonna have all this stuff just equals A. Okay. Now, if I take my equation, like equation 1, equation 2, equation 3, and I add them all together, this is going to get me, what is this? This one, this one, this one. We're going to get Fp minus F21 plus F12 minus F32 plus F23 equal to all of these together. So this is M1A plus M2A plus plus M3A. Okay. And before, right, we said that, for instance, block 1 feeling block 2 pushing back on it, that's the same force that block 2 feels block 1 pushing on it. So F12 is equal to F21. So if I have, for instance, here minus F21 and then plus F12, these are the same thing. So the negative of something plus the positive of something, this just goes away. Get rid of these. This goes away. And also the same thing here. F32 is going to cancel out with F23. So all we're left with is now that FP, the pushing force, is equal to M1A plus M2A plus M3A, which notice how there's an A in all of these. Factor out. So this is the same thing as M1 plus M2 plus M3 times A. Okay? Which is the same thing as we did here. When we did the sum of the forces, and we did this as like one big supermass. So remember, like, if we treated this as a supermass, this was just the pushing force equal to 50 newtons was equal to M1 plus M2 plus M3, the mass of them all together, times some acceleration. And then that's how you could solve for it. That's the same thing we got when we did it here. It's just that's a nice shortcut. That's where it comes from. Cool. All right. So let's then apply that to this question, which a little bit trickier because now the blocks aren't just moving, you know, like left, right to each other. We have like one on top of the other. Okay. All right. Okay. So we have the 3 kilogram block, okay, here, and then we have the 5 kilogram block. And let's draw some forces. Okay. So I know that the 5 kilogram block is going to be directly pulled with 5 newtons to the right. So this is going to be equal to my force pulling, which is, well, we're going to solve for that. And then we have to think what other forces are acting on this. So friction is the one that's going to be kind of tricky here. Okay. So the 5 kilogram block, and this is the important thing about friction. Friction always opposes the motion that something wants to go. Okay. So this 5 kilogram block would like to just kind of like stay still, right? But it's being pulled to the right. So friction will oppose that change where it's trying to go. So in this case, the 5 kilogram block and the ground are going to have frictional forces between. And so this will end up feeling a force of friction to the left. Okay. From between the, this is between the 5 kilogram block and the ground. Okay. Additionally, right, this 5 kilogram block is going to have a normal force, has to have a normal force. Anything that's resting on a surface is going to have a normal force. Normal also means like 90 degrees, so it's always going to have a force that's perpendicular to the surface. And it's also going to feel the force of this 3 kilogram block on it, okay? So we would say that the 5 kilogram block, because it has something on top of it, is also going to feel, we're going to say F of, let's call this block, I'll call this block 3, I'll call this block 5, just, I'll call them by the masses. So this is the same thing as F 3 on 5, okay? All right, yes. And then here, there's one other thing that happens. Yeah, okay. Because this thing is being pulled below this 3 kilogram block, it's also going to feel a force of friction trying to pull it back in terms of the friction from the top block on top of it. So this is also, this 5 kilogram block is also going to feel the force of friction pulling it to the left of between the 3 kilogram and the 5 kilogram. Okay. So now let's look at the 3 kilogram block, okay, separately. So the 3 kilogram block is going to have its own normal force. So we're going to call that, here, let me call this FN5. And F35, force friction, that's fine. Okay, cool. Let's call this Fn3, the normal force of the third block. Okay. It's also going to have, right, a force of gravity. And let's see, this thing wants to stay still, right? And then as this 5 kilogram block is being pulled to the right, it's trying to drag this thing to the right as well. And so what's going to happen there is that friction between the 3 and the 5 kilogram block is actually going to pull to the right here. This is the force of friction between the 3 kilogram and the 5 kilogram. And then additionally, there's a force of tension pulling it to the left, which is keeping this thing stuck against the wall. Okay. Now, this is where the force pairs come in. See, for instance, how the force of friction between the 3 and the 5 pulling it to the right is going to equal the force of friction between the 3 and the 5 that the 5 feels. The 5 kilogram block, because it's getting pulled to the right, is going to feel friction trying to pull it to the left. The 3 kilogram block is going to feel friction trying to pull it to the right as this one like gets pulled to the right because it's trying to like drag it with it. If, for instance, we didn't have a rope attached to this 3 kilogram block, like let's just say this was just like floating free and whatnot, you can think of it as like the 3 kilogram block would like to stay still, right? It would like to stay still, but it's getting pulled. If it's stuck to it, it's having an acceleration to the right. And in order for there to be an acceleration to the right, there has to be a force to the right. And it's not this force that's acting on the 5 kilogram block. That's directly hitting the 5. The force that pulls this 3 kilogram block to the right is actually friction. The friction between the 5 and the 3 is what pulls the 3 to the right. And opposes the motion of like where it's trying to stay. It would love to just stay there. It would love to stay still. But it's getting pulled to the right. Okay, cool. But we actually do have a rope attaching these. These two are going to be equal. And then there is another key thing here, okay, which is that this normal force that the third block experiences, this is technically the force that the third block feels from its surface, which the surface of it is the 5 kilogram block. So this is the same thing as like F of 5 on 3, which excuse me, this is equal and opposite to the force that the 5 kilogram block feels from the 3 one, which is F3 on 5. So I'm going to call this F5-3, I'm going to call this F3-5, and then these are technically equal. Okay. And then this, yeah, this is the force of gravity. This is just the... All right. Next thing to do is to do the sum of all the forces for each block in each direction. That's, you know, the hardest thing in physics is drawing this diagram. Once you have this diagram, it's just algebra, and you just have to make sure you keep all the algebra straight. So if we look at the sum of the forces in the y direction for this block, okay, we have this one pulling up and this one pulling down, okay? So that's equal to F5-3 minus the force of gravity, which is going to be, what's that? That's 3 times 9.8. And then this has to equal 0 because this thing is not moving up or down. So remember, sum of forces equal to mass times acceleration. If this is 0, then the forces up, down have to cancel each other out eventually. If we look at the sum of the forces in the x direction, however, we have the force of friction between the 3 and the 5 block pulling to the right, and then we have the force of tension on this rope keeping it stuck to the wall, and that also has to equal 0 because this thing is not accelerating. Okay. Same thing here. Let's look at some of the forces in the y direction. So I have the normal force for the 5th block, okay, minus F3-5, okay. This also has to equal 0. It's not moving up or down. And then the sum of the forces in the x direction, okay, so this is going to be the pushing force minus the force of friction between the 3 block and the 5 block, right? Minus these friction. But also minus the friction between the 5 kilogram block and the ground. Okay, so this F friction, let's just say like the ground. Okay. And let's see, what do they want to know? They want to know assume I'm pulling the bottom block out from with a slow constant speed. Okay. Constant speed means acceleration is 0. So this also has to be equal. Hey, Newton's second law. Hey, what's up, noise? Right, okay. So now we have our equations, but we have a lot of variables here, and, what we want to do is try to simplify these equations into things that have the same variable, because then we can start to cancel stuff out. Notice how everything here equals 0. So technically, all of these equations equal each other, right? Because they all equal the same thing. They all equal 0. Okay. The first thing you kind of want to do when you see these is to rewrite these frictional forces in terms of the normal force and some coefficient. Because what we know is that the force of friction is always equal to, in this case, because things are moving, this is going to be mu k times the normal force that's acting on the. Okay. If things are stuck, this ends up being mu s, but we know that this is sliding out to the. Okay, so for the friction between the 3 and the 5 block, right, which is here and here, this is going to equal to the normal force of the 3 block, which is Fn3 times mu k. Okay, we do know mu k. I'm not going to put the numbers in yet. I'm just going to use symbols. I have a joke. Why did the cat fall off the floor? Why did the cat fall off the floor? Wait, how do you? Oh, fall off the roof. Oh, why? Why not? Yes, normal force. But here's the other cool thing: the normal force on this block is also the same thing as F5.3, same thing as F3.5. So I'm just gonna call this F5.3, because what we're doing is we're now having things where we have the same variable. All right. Same thing here. Instead of F3.5, I'm just gonna call this F5.3. Now we have same variable in all things. Fn5, I can leave that as that is. And that's going to come into play when we talk about the friction between the 5 kilogram block, the bottom block, and the ground. That, which is here, force of friction in the ground, that's going to end up being the normal force of this block, which is Fn5, times mu k. All right? Oh, and then cool here, look, force of friction, right, between the 3 kilogram and the 5 kilogram block, that's the same one as the one up here. So this right here is the same as this. It's just in opposite directions. Notice how, like, this one is positive. This one. So this is going to end up being F5.3. Okay. Okay. Cool. All right. What do they ask for? What is the frictional force between the bottom block and the floor? Okay. Well, the frictional force could end up being this. So for part A here, say Fn5 times mu k is going to end up equaling where is it? Oh, you know what? We forgot one more force here, actually. This technically also has the force of gravity. I guess think so. We technically also have, this is the force of gravity. Right, which is, that's going to be 5 times 9. Okay. Yes. Okay. 4 equations. How many unknowns do we have? 1 unknown. 2 unknowns. 3 unknowns. 4. Okay. Technically, we have 4 equations and 4 things we don't know. We can technically solve this. In algebra, as long as you have the same number of equations as the things you don't know, solve for things. So let's think of like some clever ways to get rid of here. There's a mute. Okay, very cool. We can solve right away for what F5.3 is by using this equation, because this only has 1 unknown in it. Right? See how we just have 1 unknown and we have a number here? This tells me right away Yeah, okay. F53 is going to equal to 3 times 9.8. Let's just use 10. Let's just use 10 for everything. Make things nice. Say this is 10. This is equal to, okay. Which now, okay, I can plug into here if I wanted to get the tension. I don't need the tension yet, right? I can then just plug that into here to then get the normal force on 5, okay? So Fn5, if we move these all over, right, that's going to be equal to 30. Then here, we'll just call this 50 plus 50 and equal to 80 newtons. Okay, cool. Which then I can plug into this equation to get pulling force. So we're going to, F pulling is going to equal F5 on 3, which said was 50. That's 50 times, and I think mu k was what? They say mu 0.3. Times 0.3 plus Fn5, which we said was 80 times 0.3. Okay, cool. So the pushing force ends up being 15 plus 24, which should be equal to 39 newtons. Curious. Because there wasn't enough mu? Dude, that's too funny, man. Okay. Could be another mu. Uh-huh. That's the top block. Okay, and then let's see what the force is between the two. So that was equal to this one, F of friction 5. Okay. Yeah. That's easy. F35 we said was 30. So the force of friction between the two blocks, that was 30 times 0.3. So that's about 10 newtons. That's we got that right. So between the two blocks, that's going to equal to 10 newtons. You know that, okay? Force between the bottom block and the ground, that's going to be, that was this one, Fn5, right? Going to be, that was Fn5, right? So that was 80. 80 times 0.3, so that's 24. That one's correct. I agree with that one. Uh-huh. Okay. And then the total pushing force to pull this out is going to be equal to the sum of the two, right? Is, oh, I wrote a 50 here. Sorry, this should have been 30. Sorry. There we go. That's where this goes. 10. This is 34 newtons. Okay. Little typo. But yeah, that's correct. That's how you do that one. Oh, that one's a bender, dude. Oh, man. Anyways, hardest part of this question is always just drawing the force diagrams, okay? Again, please ask me if you ever have, like questions on, like, how you draw these force diagrams. The most important thing is to talk about each block in its own. And, like, don't worry about, like, other forces that are acting on other blocks. So, in the case of the top block, I don't write this force that's acting on the second block. I know, like, indirectly, me pulling on the bottom block will do something to pull on the top one, but it's not directly that F. That force gets transferred through the friction between the two blocks. That's what this was, this force of friction between them. These questions would be beyond me. No, noise. These are not beyond you, dude. These are pretty. This is the upper end of mechanics, but it's not too bad. Dr. Gold, have you ever smoked a cigar? I have. They're cool. They give me headaches, though, honestly. Like, it's like too much nicotine. Whatever. But it's cool to look cool, I guess. Actually, when I was in undergrad, my TA for my physics lab was like super into like pipes, you know, like the tobacco pipes and whatnot. He was like super old school, like almost like steampunk type guy. Yeah. Yeah, it's cool. I'm Dr. Goldstand. Life what? I'm a Dr. Goldstand for life. Def looks cool. Yeah, no, these are cool questions. You know, these are cool physics ones. We have 65 views on the TikTok. People find the streams. It's okay. I didn't expect many people in the Discord to honestly like watch this part because this is beyond a lot of you guys. It's okay. Defo looks cool. Let's see. What else? What else? Question? Yeah, these aren't too bad. If there are any like cool questions on the. If you ever noise, if you want to like see like an example of like how AP Physics questions are asked, like please, like we have a whole course here we built. Go through stuff. So what's the simple harmonic motion? See what other questions I have. Ooh, this is a good one. I actually kind of like this one. Paste it. Cool. All right. Says a horizontal spring is on a frictionless surface with a spring constant of this and a mass of this. If the spring is stretched 2 meters past its point of equilibrium and released, how many times does the mass pass through the per minute? They're trying to screw with you here with different units here. Okay. So we have spring attached to mass. K here is equal to 10 kilograms. And it's stretched an additional 2 meters. And they're asking how many times does the mass pass through equilibrium per minute? Okay. So this thing is going to go back and forth, right? And actually, so this is actually kind of if we were to make a graph of this, right? Let's say that like it's going to start at 2 meters here. It's then going to go through the equilibrium. It's going to hit the compression stage where it's at the maximum compression. It's going to come back through the equilibrium, and then it's going to come right back to where it started. Okay. So this is actually kind of this is almost a trick question here. A lot of times I think students would see that, you know, how many times does it pass through minute, and they would think that this is frequency, but technically not correct. This is actually going to be 2 times frequency. Because what happens in a single period the mass on our spring here is going to pass through the equilibrium position. Equilibrium is where the delta x is equal to 0. It's going to do it twice. Okay. So whatever I get for the, and this is always frequency is equal to the number of cycles, really, cycles. So we have a couple variables here, right? I have delta x, I have k, I have m. K is equal to 10, delta x is equal to 2, then m is also equal to 2. And I would like something that gives me like the period or the frequency. Well, what I do know, right, is that the period of oscillation, right, is equal to 2 pi square root of m over k. Okay. So you can see here, I actually don't care about delta x. We don't even need it. We can get rid of this. This is actually extra information. It's kind of like a red herring. They're trying to mess with you. We just need the mass and the spring constant. So this is going to be equal to 2 pi square root of 2 over 10. So that equals to 2 pi square root of 1/5. Okay. Calculator. So this is going to be 2 times pi times square root 5. That's going to be equal to 2.8 seconds. All right, 2.8 seconds. Now, what you know about period and frequency, right? Because this is the amount of time in a single period, okay? And so we know that it's going to cross the equilibrium 2 times in 2.8 seconds. So here's what I can say. I can say, like, there are 2 crossings in every 2.8 seconds, okay? And this is where, like, stoichiometry kind of comes in handy here. Because what I actually want to know, right? So what I'm asking for is how many, what do they want? They want how many crossings in a minute. So they want to know how many crossings in 1 minute is equal to 2 crossings in 2.8 seconds. So all I have to do here is I have to convert seconds into minutes. And the way to do that is to use a conversion factor where I'm going to say, oh, there are 60 seconds in 1 minute. So now look what happens with the units. This is the beauty of stoichiometry. Stoichiometry is so cool. I love it. These go away, right? Goodbye. And now we're just left with crossings per minute. So this ends up being 2 times 60 all over 2.8. Okay. So we have 2 times 60 divided by, and then that gives us 42. Per minute. Yeah. Yeah, I believe so. Okay, cool. And it was 21. Is it 21 though? I think it's 42. Yeah, no, actually there's an error in this question actually. This one should be twice. Because it passes through the equilibrium twice in 1 hertz. Yeah. This is actually 42. Ah, I found a bug. I found a bug in the questions. Cool. Okay, let's see. Ooh. Yeah, that's that. Noise Noise says, I've never actually learned simple harmonic motion. I've just heard it's pretty tricky. It's not that bad, honestly. You know, it's simple harmonic motion just has to deal with things that oscillate back and forth. Like lots of things oscillate back and forth. Pendulums, the ocean, like waves, even like orbiting is simple harmonic motion. Is kind of a cool thing. If you think of cool, one second, diagram. Sine and it's all about just sine and cosine and like here like circle Yeah, here's a cool little video. Got it. Yeah, this is how like sine and cosine works. You can see that as like you rotate around a circle, the y coordinate pulls out this thing called sine like this. Yeah, it's super cool. Sound on it. Yeah, but basically, if you go around a circle at a certain speed, like if the angle is changing at a constant speed, the y position will change as a function of sine, and the x component of that circle will change as a function of cosine. It comes down to yeah. So if for instance you were to like take this and like rotate it around at a constant speed, okay? If theta is changing at a constant speed, then if you mapped out what the x component is of this radius, you know, going around, this is always, and let's say this is r, and this is theta. This, which is the x component, is equal to r cosine theta. And then this, the y component, is equal to r sine theta. And so, yeah, the sine of an angle, right? The y position of an angle follows a sine curve. When in the unit circle, r is equal to 1. So that's why this ends up just looking like this. So as you rotate around in a circle, you get a sine graph. Look at the y component. If you look at the x component, you end up getting a cosine. It's pretty cool how it all comes from. Yeah, that's all it really is. Yeah, it's stuff just oscillating this way. And, you know, different properties in physics, such as the mass or the spring constant or gravity, they affect basically, you know, how compressed this is or how like stretched it is, you know, amplitude and frequency. Yeah, it's cool stuff. Okay, I think we're going for a while, hour 20 minutes. It's okay. Any other questions? So, assume everyone's good from that. Okay. Cool. All right. Thank you, everyone, for coming to the AP Physics 1 review session. Hope you guys got something out of that. If you have any questions, please feel free. You can post them in our Discord. I'm happy to answer anything. You know, if you're like confused about a certain topic or whatnot, let me help you out. I'm happy to go through them and whatnot. Haven't checked out our live review course on Kudu, please do. The questions are there. They're free. Run through them and get some extra practice in. FRQ sections are very good. They have all these previous exams. Like, ever want to do what a long stream? Yeah. Well, not as long as yesterday's. Yesterday's was even longer. But if you go to just College Board. College Board has them. You go here, you can see they have all the way down to like 2016. You can do all these free response questions, and they also have the answers. So feel free to look at them, and if you're confused, you know, just ask me. Just keep in mind that they did change the subjects that were on this exam. So for instance, if we look at 2016, they had circuits on this one, and circuits are not on the AP Physics 1 exam for this year. So just keep that in mind, that if you go to the later years back, you know, 2016, whatnot, yeah, it's just watch. Some of the subjects aren't even covered on the exam. Always refer back to like what the guideline is. Want to play me in chat? No, you're so good. All right, cool. All right, awesome. Good luck on the exam. If you have any other questions, please feel free to send me a DM. Otherwise, enjoy the rest of your weekend. Noise. Don't get too hammered. You know, Dr. Gold, the top man for chess. I don't know if I'm the absolute top man for. We do have, yes, and you know, if you haven't already, please join our Discord. We have we do these streams you know, 3 times a week. If you ever want any sort of help in, we're basically like a free tutor. You can go to our Twitch streams that we have. We're also going to be streaming on TikTok, but we're also going to be streaming. Oh, I can hear myself twice there. But oh, this becomes fun. It's an infinite loop of Dr. Gold. But this is our channel. Well, but here, yeah, this is our whole stream, and we do these, you know, 3 times a week. You can come ask any sort of math or science question. I'll teach you triangles, whatever you want. It's chemistry, statistics. We do it all. So please, you know, join our Discord so you can find out when these are. We have like fun events and whatnot. We give away prizes, Discord Nitro, all types of gift cards. And yeah, make this 5 times a week. I don't know. I'd be a little tired if I was streaming 5 times. 3 times for now. Yeah. Okay. All right. Thank you very much, guys, for joining. I hope you guys have a great rest of the week, and I will see you guys for our regular office hours stream tomorrow. It's gonna be at 3 p.m. Pacific, 5 p.m. Central, 6 p.m. Eastern. Till then, I'll see you guys around. Peace.